In this lecture, we'll define Gaussian curvature and mean curvature of a regular surface in R3. Let us begin. Let us take a regular surface S in R3. And let us take a point P belonging to S and D and P from tangent space of S to tangent space of S at the point P be the shape operator where this N, it is a map from this S to S2, is the Gauss map. First, let me define Gaussian curvature of the surface S at the point P. So, what is Gaussian curvature at the point P? So, you have this D and P, which is a linear map. So, I'll get a matrix of this linear map. And if I take the determinant of that matrix, so that will be called to be the Gaussian curvature. The determinant of D and P is called the Gaussian curvature of S at the point P, and it is denoted by capital Kp. And now let me define mean curvature. The negative of half of the trace of the matrix obtained from D and P is called the mean curvature of S at the point P, and it is denoted by HP. Okay. So in the previous class, so we have obtained principal curvatures and principal direction. Okay. So now suppose if K1 K2 are principal curvatures of S at P. So then this minus K1 minus K2 are eigenvalues of the operator D and P. So Gaussian curvature Kp, which is the determinant of the matrix of D and P, it is equal to the product of the eigenvalues. So this is equal to minus K1 times minus K2. So which is equal to K1, K2. Okay. So therefore, the Gaussian curvature Kp is equal to product of the principal curvatures at the point P. And now if I take mean curvature HP, so this is equal to minus half of trace of the matrix of the operator D and P. So trace of this matrix, which is equal to the sum of the diagonal element of the matrix, is equal to sum of the eigenvalues. So this is equal to minus half times minus K1 plus minus K2. So this is equal to K1 plus K2 divided by 2. Okay. So therefore, this HP is half of sum of the principal curvatures at P. Okay. So now let us analyze the definition of this Gaussian curvature. So in order to do that thing, so I'll take a point P on the surface and classify that point uh, by classify the point by taking the Gaussian curvature at that point. So we'll determine the point by the way that this Gaussian curvature, whether it is negative, positive, or equal to 0. Okay, so let me write down. Classification of points on a surface. So a point P of a regular surface in R3 is called elliptic if the Gaussian curvature Kp is greater than 0. Okay. So for example, so if I take the unit sphere S2, so Kp is greater than 0 for all P belongs to S2. Okay, so all the points in this S2 are elliptic. Okay. Second, hyperbolic. So this point P is called hyperbolic if Kp is less than 0. So in the last class, we have seen that if I take this hyperbolic paraboloid, z equals to y square minus x square. So then so this K1, this principal curvature K1 at P, so P, let us take it to be the origin. So this K1, it was greater than 0, and K2 of P, it was less than 0. So therefore, this Kp equal to K1 multiplied by K2, it is negative. Okay. So this implies that P is a hyperbolic point. Third is parabolic. So this point P is parabolic if the Gaussian curvature at the point P is equal to 0 and the linear operator dnp is not a zero map. Okay, so dnp is not equal to 0. Okay, so again in the last class, so we have done this thing. So you take the cylinder, which is x square plus y square equals to 1. And xyz, it belongs to R3. So we have obtained the principal curvatures to be the following. So one principal curvature K1, it was equal to 0, and another K2, it was not equal to 0. So now if I take the product of this principal curvature, so this is equal to 0. And because this K2 is not equal to 0, so this implies that the NP is not equal to 0. And this is true for all P, for all P on the cylinder. So this is true for all points on the cylinder. So all points on the cylinder are parabolic. And the fourth is this point P is said to be planar if this operator D in P is equal to 0. Okay. So for example, so every point on a plane is planar because the Gauss map, it was a constant map. So differential of that map, it is equal to 0. Okay. So now let us observe this thing. So in terms of local coordinate, so what will be the formula of this Gaussian curvature? So let U sigma be a surface patch in S. Okay. So what is my first fundamental form? The first fundamental form is given as E du square plus twice F du dv plus G dv square. And second fundamental form is given as L du square plus twice M du dv plus N dv square. Okay. Also, in the last class, we have obtained this thing. So matrix of T and P, so this is equal to minus inverse of this matrix EF FG multiplied by the matrix LM M N. So which is equal to minus 1 by EG minus F square multiplied by the matrix G minus F E multiplied by the matrix L M M N. Okay. So therefore, so the determinant of the matrix D and P, which is equal to the Gaussian curvature, so this will be equal to Ln minus M square multiplied by Eg minus F square whole divided by Eg minus F square whole square. So this is equal to Ln minus M square divided by Eg minus F square. And the mean curvature, so HP, so this is equal to minus half of trace of the matrix D and P. So which will be equal to 1 by 2 times Eg minus F square multiplied by GL minus twice Fm plus En. Okay. So we have an explicit formula of Gaussian curvature and mean curvature in terms of the coefficients of first fundamental form and second fundamental form. Okay, so let us now do a concrete example. So let us take a torus. So we'll be finding Gaussian curvature of a torus. So let us take a parameterization. So let sigma ub is equal to a plus r cos u whole multiplied by cos b, comma a plus r cos u whole multiplied by sin b, comma r sin u. So where 0 is less than u less than 2 pi and 0 less than b less than 2 pi. Okay, so in order to find the Gaussian curvature, we should find the coefficients E, F, G, L, M, N. So E is equal to the inner product of sigma u with sigma u. So I'm not doing all the computation. So this inner product, it will turn out to be equal to r square. F, it is the inner product of sigma u with sigma b. So this will turn out to be equal to 0. So G is equal to the inner product of sigma u with sigma b with sigma b. So this will be equal to a plus r cos u whole square. Okay, so here also note one thing. So this r is a positive number which is less than a. Okay, so now we need to find this L, M, and N. So how to obtain those coefficients in a faster way? So let us check this thing. So if I take any two vector and take the cross product and take the norm of this, so norm of a cross b whole square is equal to norm a square times norm b square times sin square theta, which is again equal to norm a square times norm b square minus norm a square times norm b square cos square theta. So this is equal to inner product of a with a multiplied by inner product of b with b minus inner product of a with a multiplied. No, so this is not needed. So this norm a square times norm b square times cos square theta, it is the square of the inner product a and b. Okay, so we have this thing here. So therefore, if I take the square of this cross product sigma u cross product with sigma b, so this will be equal to inner product sigma u with sigma u, inner product sigma b with sigma b minus inner product of sigma u sigma b square. So this is equal to E f minus g square. Okay, so this implies that norm of sigma u cross sigma b, so this is equal to root over EF minus g square. Okay. So also observe this thing. So suppose I have this three vectors. So A is equal to A1, A2, A3. B is equal to B1, B2, B3. And C is equal to C1, C2, C3. Then the inner product of A cross B with C, which is equal to the dot product of A cross B with C. So this is equal to the determinant of C1, C2, C3, A1, A2, A3, B1, B2, B3. Okay. All right. So now, what is my L? So L is equal to the inner product of sigma U cross sigma B divided by norm of sigma U cross product with sigma B, comma, sigma UU. So L is equal to this thing. So therefore, this will be equal to 1 by, so norm of sigma U cross sigma F, it is equal to root over EG minus F square from here. Yeah, so it should be EG minus F square. Yeah, so L is equal to 1 by root over EG minus F square multiplied by inner product of sigma U cross sigma B with sigma UU. So, which is equal to the following: 1 by root over EG minus F square, determinant of, so first row you place sigma U, and then the second row you take sigma U vector, and the third row you take sigma B. So if I take this thing, so this will be my L. And you can compute this root over EG minus F square. So this will be equal to R times A plus R cos U. And this L, it will turn out to be equal to R. And now what is my M? So M is equal to the inner product of sigma U cross sigma B divided by norm of sigma U cross sigma B, comma, sigma UB. So this, after computation, this will turn out to be equal to 0. And N, so this is equal to the inner product of sigma U cross sigma B divided by norm of sigma U cross sigma B with sigma BB. So this will be equal to cos U times A plus R cos U. So therefore, the Gaussian curvature so K of the point sigma UB, so this will be equal to cos, let me write the formula first. So this will be equal to Lm minus n square divided by Eg minus f square. So this will be equal to cos U divided by R times A plus R cos U. Okay. So now let us take the torus in R3. And we have this axis. Okay, so now let us see where this k is equal to 0. So k is equal to 0 at u equal to pi by 2 and u equal to 3 by pi 2. So if I take this circle and so this u equal to pi by 2, so we'll get these 2 points. So here this k is equal to 0 and u equal to 3 pi by 2, you'll get this below point where this k is equal to 0. And if you vary v, so we'll get this circle. So get this 2 circles. So where this k is equal to 0. Okay, and let us see where this Gaussian curvature is positive. So k is greater than 0 if I take 0 less than u less than pi by 2 and 3 pi by 2 less than u less than 2 pi. Okay, so this 2 blue circles in the torus, so it will decompose the torus in 2 components. So if I take this part, so here this k, it will be positive. And k is less than 0. So if pi by 2 less than u less than 3 by pi 2. So on this side, the back half side, this k, it will be less than 0. Okay, so therefore, what we have, so at k, the points where this k is equal to 0, so those points are parabolic points, kp equals to 0. So here in this blue circle, this k is equal to 0. So the points on this blue circle are parabolic. Okay, and now in this green part, so the Gaussian curvature is positive. So those points are elliptic points, and in the back half, so the curvature is negative. Okay, so those points are called to be hyperbolic points. Okay, so we'll stop here.